So the last thing we talked about was this limit lemma, and the limit lemma gave us a nice characterization of all of those sets which Turing reduced to zero jump. And it seemed pretty useful. We know that amongst all those sets, right, amongst all those sets reducing to zero jump, are included all the CE sets. And so the next little bit of work is to come up with a criterion which allows us to recognize the CE sets in between those. Now, of course, you know how to recognize a CE set, because a CE set is just a domain of a Turing machine. But what we want is, or what we'll get, is a way of saying, okay, if we have such a delta 2 set, it is a CE set if the following additional criterion holds. So that's the next little bit of work towards. The first thing to do for this is the modulus lemma. The modulus lemma essentially is one of the two implications you need for this characterization. This says that if B is a CE set and A Turing reduces to B, then A is the limit of AS for computable AS. Right? This you knew. Because if you Turing reduce to a CE set, then by transitivity of Turing reduction, you Turing reduce to the halting problem. Therefore, your delta 2, therefore, there exists an approximation AS like this, such that you're the limiter. But additionally, from the information that you reduce to this particular CE set B, we get that also it has a modulus n which Turing reduces to B. So if you Turing reduce to something, there exists among the many different computable approximations for this AS, there exists at least one whose modulus is Turing reducible to B. So we have to prove this. How are we going to prove this? Well, we're going to prove this in a way that in the limit lemma there was this one, must be my lucky day, I found a dime. In the limit lemma we found in the implication 3 implies 1, right? If you Turing reduce to the halting problem, then you are limit computable. In there we had this way of obtaining from a reduction an approximation. And I promise you, this is the first time you see this. You might be a little surprised that we did it like that, but we're going to see it more often. Well, here is the first time. So if we have B a sigma 1 set, then in particular it has a sigma 1 approximation BS, right? A computable sequence of approximations that is increasing. Right? That was the sigma 1 approximation. The sigma 1 approximation was the delta 2 approximation that was increasing, therefore a little nicer. Then from this we can just in that same way define AS to be those x such that x is less than or equal to s, such that phi e b of x is equal to 1. Right, where E is the Turing reduction, or the index of the Turing machine that gives you this reduction. Now, of course, this is uh, not a computable approximation, because the set B, right, it's CE, it doesn't have to be computable, therefore you can't really compute this last part, which is where I left open a little bit of room. But this is kind of the idea, right? You look at those things, you put a bound on there, so that you always have finite sets, and those that are computed by this reduction to be in there. Because you can't compute it, we just restrict it in the obvious way. So this is now the second time we see this square bracket S notation. And square bracket S just means in this whole expression, compute everything only for S steps. Which means in particular that instead of B, you use the S member in the approximation. And for this whole thing, you do the computation only for S many steps. Right? And now what we get is, of course, that before, without the S, we had all of our approximations up to S being exactly right. And now we get some fluctuation there, because these BS, they change around a little bit. Well, they grow, but them growing still means that at one point you ask an oracle question in this computation and you get a no answer. And then you stop computing. The next point, you get a yes answer to this, and you ask a much larger oracle question. This much larger oracle question isn't answered correctly by BS, but it might be answered correctly only by BS plus 481, a lot later. And then finally, this answer again switches to yes, and then you start asking about, again, a much larger kind of thing. So in principle that doesn't stop, but in practice it does. So in principle this problem or this thing about which oracle questions you ask changing along the way could result in divergence. But it doesn't, because we know that phi E with oracle B is a total function. It computes the characteristic function of A. So it is total. So at some point you get to a stable set of oracle queries, and the computation holds, and you're all good. So I guess I just argued that this is an appropriate approximation for A. Let me argue this again, because some of you look a little less happy than I would like you to look at this point in time. So why is this a correct approximation, right? Look at a particular x. This particular x is allowed to go in and out of the AS many times, right? We're not claiming that these AS are a sigma 1 approximation, they're just a delta 2 approximation with a modulus. Well, I haven't said anything about the modulus as, but so for this particular x, from some point on, this approximation needs to be correct about it. So now we need to figure out, well, when is this point? Well, we know that for this particular x, if I look at phi E B of x, right, this is either 0 or 1, and this holds and computes it correctly. Because it holds, there is only finitely many oracle queries that it asks. And so as soon as your approximation BS is correct on these finitely many oracle queries, this computation is exactly the same. Now you might need to go a little further, because this S might still restrict you from computing long enough. So as soon as these finitely many oracle queries are answered correctly, and S is big enough to have this computation hold in as many steps, then the AS are correct about this X. Okay, so we have a nice approximation, and notice that the argument I just gave was exactly the argument I gave in the last 10 seconds of the previous lecture, which is why it's good that I spend 5 minutes on it now. So we have an approximation, and now the claim is this approximation has a modulus which is Turing reducible to B. Right? Not least modulus, because least modulus might be a crappy kind of thing for this approximation, because it's a delta 2 approximation, not a sigma 1 approximation. We want a modulus that says, from this point on, is correct. And I secretly already argued about this modulus in the proof just now. As you'll see when I write it down, this modulus is the least s such that there exists a z less than or equal to s. The z is going to be the use of the computation, such that for all y less than or equal to x, we have that phi e of b restricted to z of y in s steps converges. Right? The square brackets s now also says for this b restricted to z, we use the s approximation to b. Right? Square brackets s means everything in the preceding expression done for s steps. And b restricted to z is equal to bs restricted to z. Right, it's the first stage, such that the stage is bigger than the use. Just again, a nice restriction. I guess if you restrict it as in sort of a natural, obvious way, then a computation whose code is less than s could not ask oracle questions bigger than s anyway, so it's kind of automatic in here maybe, but there exists a z which bounds the use of this computation. Well, it doesn't bound the use of all the computations up to and including x. Each of these computations holds in s steps. It uses the oracle bs up to z, and the oracle bs up to z is correct. Right? This last thing is the only thing where you really need to have the oracle b in order to check it. And notice that that's exactly what we did before. When I argued this was correct for a particular x, I said, well, go far enough out until the part of the oracle you use has stabilized to the right values. So that's exactly what this says. Go far enough out until you find a large enough part of b has stabilized to its correct values, and then compute from that part of the oracle. So that argument shows that this is modulus, and it's clearly b-computable. Right? Z oracle queries allow you to answer that question. Good. Everybody happy? Questions? Complaints? As usual, which part, if there is something fuzzy, ask me. Okay, so then we are halfway there to coming up with our criterion, appropriately named the modulus criterion. And so this says A has CE degree if and only if A has such an approximation which modulus and Turing reducible to A itself. In the AS I didn't write it down, but of course the sequence AS is supposed to be a computable sequence. Okay, A has CE degree, to remind you. Degree has many sets in there. Some might be CE, some might not be CE. But a degree is a CE degree if it contains at least one CE set. So A has CE degree, says A might not be CE, but its Turing equivalent to a CE set. So there exists a set B, which is CE, such that A is Turing equivalent to B. Right? That was the definition. And then with the modulus lemma, we immediately have the left to right equation implication, because A Turing reduces to this B. Therefore, there is this approximation with the modulus which Turing reduces to B. But B also Turing reduces to A, so anything which Turing reduces to B also Turing reduces to A. So A has CE degree does imply that there exists this computable approximation which fluctuates a bunch of times. But its fluctuations can be computed from itself, or bounded from itself. So that leaves just the right to left implication. If A is limit computable through an approximation such that the modulus of this approximation is computable from itself, then we should be able to prove that it's a CE degree. Not that A is CE, but that there exists another set which is CE, which is equivalent to A in information content in Turing degree. Pretty good with this so far? So now of course, in this kind of proof, you're always in a little bit of a bind, because now what we have to prove is there exists a set C such that, and so we just need to come up with the right set C, and the right set C is at first might seem a little bit out of nowhere, but when you sit back, have a cup of coffee, think about it, then you'll see that it is a fairly reasonable kind of set to look at here. So C is called the chains set of A, and it consists of those pairs x comma s, such that there exists a t greater than s. Right? The x comma s is going to say something about the member x and the time s, and what it is saying is, for this s, there exists a time later where the approximation changes. So this is as of x is not equal to a t of x, right? A pair xt, a pair xs is in C if at stage s, well, the approximation might be correct or not, we don't know, but at stage s, it hasn't stabilized yet. It's going to change later on. Now, of course, if it changes twice later on, then it was correct after all, but this is the set we care about. Okay. Nice enough. What do we need to see? Well, first of all, it better be CE, otherwise it could never satisfy our purposes. Well, and then you look at it and you see it's obviously sigma 1. There is one existential quantifier over something computable. Right? So it's a sigma 1 statement. Sigma 1 statements correspond to CE sets. So this is a CE set. Good. Right. So then we need to see that this CE set, well, A reduces to it and it reduces to A. Right? This is the CE set we want to show as equivalent to to A, so we need both of those. Let's do the C reduces to A first. Well, C is equal to xs such that there exists a t, s is less than t, is less than or equal to m of x, and asx is not equal to a t. X. Right? We happen to have a modulus lying around, and we know after the modulus, after m of x, the approximation isn't going to change its mind about a of x anymore. So this t can never be bigger than m of x. Therefore, we have a nice bound. And now you notice that this here, this whole expression is now computable in m. Right? If you know m, then you just need to check finitely many values. And for these finitely many values, you need to check something computable. So the whole expression here is computable in m. Therefore, computable in A. Right? Under our assumption. So that shows that C Turing reduces to A. We're halfway there. Well, then we just need to see that also A Turing reduces to C, and that happens to be particularly easy. What you need to do is, using C, you need to decide membership in A. So given a particular x, using C you want to decide whether x is in A or not. Well, for any x, at some point the approximation stabilizes. What that means is that for every x, if the second coordinate is big enough, you're not in C. Right? And also, right, as soon as you have x comma s in there, then you have x comma s minus 1 also in there. Because either between s minus 1 and s it flipped, or between s minus 1 and t it also flips. So I guess what I'm saying is in the second coordinate you have finite initial segments. For every x, there is a finite initial segment of the natural numbers which appears in the second coordinate. And so for a given x, what you do is you look for a sufficiently large second coordinate such that it's not in there. If this x comma s is not in there, then you know that after stage s the approximation won't change anymore. So at stage s you have the correct approximation. And therefore you can decide membership in A. Right? So you just, more concretely, you have your x, you start wondering, is x comma not in C? Is x comma 1 in C? Is x comma 2 in C? Is x comma 3 in C? And you keep doing this. You keep asking these questions, which you can because you get to use C as an oracle, until the answer is no. And when the answer is no, you know a level of the approximation of A which is correct. And so you can decide membership in A. Which is pretty nice because it gives us a characterization in terms of these delta 2 sets, or of these delta 2 approximations for when something is CD. Okay, so these are very important observations which we're going to use a lot later on. But we're going to do a little detour before we get to this. Right? We know in the end what we're aiming for are understanding the structure of the Turing degrees. Now we've made some characterizations. In this understanding the structure of the Turing degrees, there's this key method of priority arguments, and now we're kind of collecting together bits of information which are going to allow us to complete certain priority arguments later on. These characterizations are going to be important at some point, but not right now. The next thing that happens is that we start looking at some effective topology. Now, I'm well aware that not everybody knows topology to the same degree. So, instead of immediately jumping in with effective topology, where we wonder about effectively open sets, effectively closed set, effective compactness theorem, these kind of things, I just want to do a quick review of topology as I see it, and point set topology. So first of all, then, is the definition of a topological space, and in this course there is going to be a couple of topological spaces that play a key role, but in general the idea of a topological space is just a pair. You have the set X, which is the space on which your topology lives, and you have a T, which is a collection of subsets of X, and it's a collection of subsets of X that you particularly like. We call these things the open sets. Arbitrary pairs like this are not topologies, of course. We need that the empty set and X itself are in T. We need that T is closed under unions, and T is closed under finite intersections. Is this new to anybody? Does everybody know this? Who doesn't? Oh, okay. Compactness. New? Not new? A little bit about compactness. Interior closure boundary. Interior closure boundary. What else was I going to say? Bare space, contour space.
What was the first one?
Bare space. Bare space, contour space. Okay, so a little bit about that. Königslemma. Does everybody know Königslemma?
So
Which
I
one?
haven't done any of this.
Okay, yes. Pardon?
Which Königslemma?
Die Königslemma. Okay, so Königslemma. Okay, so I guess everything except this definition is something I should talk about. Anyway, this definition, it's still, right, this is the definition of a topological space, which of course if I plunk it down like this, it is an entirely meaningless definition, but it is one of these cases where abstraction succeeds. Right? In mathematics, you have some people who take every notion they can find and they abstract away everything reasonable and interesting about it, and then they get these wonderful theorems which are incredibly general and also now here comes a big value judgment, of course, entirely uninteresting. All right? So these spaces, the Rn, I think everybody will agree these are interesting, important. If what you do relates to Rn, then that starts being a good explanation of why you should care about it. Right? Rn is important. Now, Rn is not just a topological space. Rn is a nice topological space because its topology is given by a distance function. And this is exactly what topological spaces are about. sort of a good starting point, where you take Rn, there's some structure in Rn which is captured by this metric function. Using this metric, you define things like B epsilon of x, which is the ball around x of radius epsilon, right? A strict inequality, not less than or equal. So these are the basic open sets of this topology. And then you start looking at the open sets of this topology, which are arbitrary unions of these basic open sets, and you find that it has these three properties. Now, according to the argument I just gave, this should not immediately make you interested in topological spaces. At least I don't think it should. But it turns out that if you study these topological spaces, many of the properties that Rn have and that other interesting topological spaces you might care about have, you kind of lay bare the real reason for these properties and the reason why they are shared between these different kind of things. And so, in that sense, the definition of topological space is an abstraction that succeeded. It's not an abstraction because we can. If you do math, often you do things because you can, right? But this is something which has been around long enough that it really has shown it isolates some key properties. I guess, like groups, right? Same thing. You care about Z with addition. You abstract away, you get a notion of group. And it turns out that this abstraction is very useful in getting some really deep insights into the structure of the things you care about. Okay. Oh, so I said open is the things in the topology. Closed is those sets C such that x minus C is in the topology. So a set is closed if its complement is open. Right? And in this sort of context, and the same intuition you should have in arbitrary topological spaces, is that something is open if for every element in it you can put around it a little open neighborhood which shows that this point is kind of away from the boundary of the set. Right? That's exactly what these open balls do, and this kind of generalizes that something is closed if the same thing is true for the complement. Okay, so there are these two sets of reals which look in some ways very close to each other, the open and the closed interval in the corresponding topology 0, 1. The open interval is indeed open and the other one is indeed closed. But they have this property which is really kind of interesting. If I draw the picture 0 to 1 and here 0 to 1 included, then in this top one I can define the sequence of open intervals. But you need to see me draw it. If you don't, and you don't know which parentheses go with which one. Right, I define this collection of open sets, which together they cover the whole interval, and not a single one can be missed. Right? So what I have here is a U, which is an open cover, which means that X is a subset of the union of U, and U is a subset of the topology. This is what it means to be an open cover. It's an infinite open cover such that all open subcovers are still infinite. And you can now try and do the same thing in this almost completely the same topological space, the closed interval from 0 to 1. And write down open covers like this, and it turns out that you're going to fail. Because 0, 1 is a compact topological space, which means that every open cover of X has a finite subcover. Right? No matter how creative you are about generating a sequence of open sets that cover this closed interval, you will not succeed at writing one which does not have a finite subcollection that also covers the whole space. Now this is another good time to wonder, so what? I threw a definition at you. Why would you care? Well, first of all, because I'm telling you that it's an important definition. It has a lot of properties. But it's also, I guess first of all, how do you see this is true? Right. 9 out of 10 of you already knew your topology, so you can quickly tell me why this is compact.
You assume it's basic, I guess, first, maybe? Basic sets in your cover, and then...
If you want to.
And then,
right? So this is the first observation to make, that the statement, every open cover of X has a finite subcover, and the statement, every open cover consisting of only basic open sets has a finite subcover or equivalent. Because basis generates the topology. And I'm not sure why it helps you, but I'm willing to accept it.
well, just that way you know you're just dealing with like simple intervals.
Open intervals?
Right? Yeah, open intervals.
Okay.
And then we'll just, I guess, you know that you have to start, right? So your first point is in there. So that there's some interval to the around 0. And then
So this is clearly the start of a correct argument, but you're not necessarily being very efficient about it. In particular, this is the type of argument that will almost certainly lead you to the conclusion, but you're not announcing me what you're about to do before you do it, right? This is one of the things which I certainly try to do most of the time, and just because I'm standing here, I can force it a little bit, that whenever you write something or whenever you're explaining something, it helps the reader or listener an awful lot if you first tell them, this is what I'm going to do, and then you work out the details. So in this particular case, you're starting to argue something which is exactly the right thing to argue, but you can be a lot more efficient about it. Right? There's one thing you can say that tells me exactly that you know what this proof is like. And what that one thing is to say, okay, look at those points in this interval such that the interval from 0 up to that point are covered by finitely many sets. Now look at the least upper bound of those points. If you make it up to 1, the whole thing is covered by finitely many sets and you're done. So towards a contradiction, assume that you're not. Now you have this alpha, which is the least upper bound of all the points that can be covered with finitely many sets. So here is alpha. So that means any point to the left can be reached with finitely many points, but no points to his right can be reached with finitely many open neighborhoods.
I just started with that line of reason just to show that alpha wasn't 0.
Exactly. Your argument shows you get started. Alpha is non-zero. So like I said, you proved something exactly right, except you weren't telling me what you were doing, showing that alpha is non-zero. So here's alpha. Now you notice that alpha is contained in one of the open neighborhoods. So there is this one open neighborhood which covers things to the left and to the right. and therefore there's this point here in that open neighborhood which is reached by finitely many. Well, finitely many plus 1 now leads you to something to the right of alpha. And that contradicts with that alpha wasn't. That alpha was the least upper bound. You found something bigger with that contradiction. This is a proof which you should have up your sleeve, right? Whenever pressed to prove it, like I just did, you should have it already. It's sufficiently basic. But the gold is like a simple version of Heine-Borel, I guess. Heine-Borel is all dimensions, but this is just one dimension. Okay. So that shows that indeed this 0, 1 is compact. Now, why do you care about compactness? Well, one of the things you get out of it, and this is another one which, if you don't immediately know the proof of this, you need to go back to your topology books. In a compact space, in a compact metric space, every sequence has a convergent subsequence. And now you wonder, why did you go back to compact metric? But you should know that as well. Okay. Compactness. Base. So this is always important. A good property of a mathematician is that you're lazy. And so instead of trying to describe all sets in a topology, you want to economize on this a little bit and just describe the sets that generate a topology. And so a base is a collection of subsets in this power set, such that if you start generating with them, if you take arbitrary unions of these sets, then you end up with a topology. Okay. So then, the two key topological spaces for the course. On the one hand, Bart space, omega to the omega, with the topology T, where T is T has. So I'm very carefully not saying which the open sets are in Bart space because it's complicated, but it has a base consisting of the sets square brackets S, which is the set of all those F in omega to the omega, such that S is a subset of F, and here S is in omega to the less than omega. Now, I just, as I wrote that, I realized that 3/4 to a half of the notations I write down for the first time, and I'm not sure if I said what they are before. Omega to the omega, this exponential notation is just a nice brief notation for the set of functions with domain omega and range omega. The domain is in the exponent, the range is in the non-exponent. Omega to the less than omega is the set of finite sequences of natural numbers, right? This less than omega denotes the domain. So some finite natural number is the domain. The range is in omega. So these are initial segments of functions. And then the square bracket S is exactly the collection of functions which extends the given initial segment. The picture being this. Right? Here is S, or the graph of S, the finite initial segment. Oh, this is omega and omega. And those square brackets S consists of all those functions which extend S, and that is the basic open neighborhood, or That's 8 choice of basic open neighborhoods for this particular topology. Notice that it's metric. By the metric, d of xy is equal to 2 to the minus delta xy, where delta x of y is the minimum, n where xn is not equal to yn, or 0 if x is equal to y, in which case this definition doesn't quite work, depending on your opinion of 2 to the minus infinity. So it's a nice metric space, which is pretty nice. The other space we care about is contour space. This is 2 to the omega with the topology, and here the topology is just generated by these same sets. But now S is in 2 to the less than omega. Now again, I need to explain myself a little bit. 2, the natural number 2 is a representative of the set 0, 1. Right? So these are 2 to the omega are the infinite sequences of zeros and ones. 2 to the less than omega are the finite sequences of zeros and ones. And again, the basic open sets are the ones where all functions extending a given finite sequence of zeros and ones. Metric space by the same topology. Difference between the two again. Barre space is not compact. Right? There's the set of functions that start with 0, the set of functions that start with 1, the set of functions that start with 2, the set of functions that start with 3. All of them together cover the whole space, and none can be left out. So this is not compact. Contour space is compact, and now you know which Koenigslemma I was talking about, the one that shows that contour space is compact, which I'm going to just start with next lecture. If you have an infinite tree which is finitely branching, then you have an infinite branch. That is, I think, the most basic version of Koenigslemma. And I think each and every one of you is creative enough to prove it before the next lecture. You should try to.